Just a really quick thing. I added this annotation I said I would last time. It's not always immediately clear that you can click on these to open up the slides. So I just added a little note there. Hey, look, this is where you click to open the slides. So today's slides are updated. I didn't change much for this one, but I'll go through the slides before each lecture. And before the lecture starts, I'll have the updated slides. I don't think much content-wise is going to change, but I'll, reorganize things a little bit better. But click right here, you'll get a PDF version of the slides. It'll open right in your browser. Homework 1 is released. That's the one that we got to talk about a little bit more. I won't go too in depth. You can read the description at your leisure. But homework 1 is going to set the foundation for your project that you're going to work throughout the 5 homework assignments. So for this one, not much in terms of features that we're going to build today, but we do want to lay that foundation. The big ones are going to be Docker, getting Docker set up to be able to run your app, and then doing a little bit of HTTP parsing. One, just to have your app say hello world or whatever you want it to say, some welcoming message. A redirect with a 301, and the big old 404 has some 404 message. So not much in terms of features, but getting the foundation of your code, the foundation of your project set up to be able to build off of for the rest of the assignments. And I'll repeat this. You'll get sick of hearing this. I'll repeat it so much. But for these first 2 assignments especially, I strongly encourage you to focus on good fundamental design practices and writing things like modular code, having methods that are more generic than specific, not hard coding things like that, to make sure that you can reuse that code in future assignments. You don't want to be redoing a lot of work in future assignments when you work on this one. So if you have a good setup and good structure, write separate methods. Don't write everything in one big main method, for example. Things like that. I strongly encourage you to start right from homework 1 with a good design, knowing that this is going to be a pretty large project by the time you're done, by the time you have all 5 homeworks done. You don't necessarily have to read the slides before class. If it's however you want to, whatever works well for your study habits. I know some of you like to open up the slides during lecture. So if I go to the next slide, you can still go back to the previous one and say, wait, what was that again? Things like that. If it helps you to read the slides before class, by all means, go for it. And that's for those of you who are reading the slides before class. That's why I'm mentioning that when the slides will be updated. You can use the slides as they are right now. They're going to be just fine, but some of them last year were a little rushed. They're not quite in the state that I wanted them to be in, so I'll be revising them and just updating them, making them better. What is modular code? Modular code is like, instead of using large methods, chopping that up into smaller methods, smaller functions if you're using a functional programming language or a language that supports that. Writing multiple classes if you're taking an OOP approach. Having a class, like we'll see HTTP requests when a request comes in. I like having a request class that's going to do all of the request parsing stuff for me. If that doesn't make sense, don't worry, because we didn't get to that lecture yet. But just writing your code in smaller pieces and then combining those pieces to do what you want it to do, as opposed to writing very large methods. I've seen a lot of homeworks last year where it was just one large method that did everything, and those students inevitably had a lot of trouble when we got to the later assignments. Yeah, Docker will be explained in lecture 2. So Docker, we're talking about on next Friday. HTTP, so everything to do the other 3 objectives, will be covered in the next 3 lectures. Today is mostly background and information about stuff that, to be honest, you won't have to do in this class. This is the one background information lecture. So Docker, I listed as the first objective because you need it for all of them, but you can work on the other 3 first. I recommend that you write your app using complete the other 3 objectives, and then when we get to Docker, you can add Docker to your project. Docker is something that you can add after the fact, so it's not going to be an issue. And then I'll give examples of Docker down here. Until what lecture is the content needed to do homework 1? So homework 1 is all about this section 1. If you collapse that, everything for homework 1 just disappeared. So everything in homework 1 is in this box. Homework 1 is the only one that breaks that a little bit, in that I will give more examples. I won't cover more content. This is all the content that you'll need for Homework 1. But this, I will give a little bit of examples that will help you with Homework 1 still. But the rest of the semester, that'll hold true. So this section for 2, that is everything you need to be able to do Homework 2, everything you need to be able to do Homework 3, etc. Okay. Let me go over one more logistical thing, and then we're going to get into some content proper. So the grading is going to be on a 0 through 3 scale for each objective. So each of these 4 objectives will be graded on a 0 to 3 based on these criteria. Either they're completely correct, mostly correct but with some issues, wrong, or you just didn't try. And those will be mapped to percentage grades as follows, right? Like this. So if you get a 3, it's 100. That one's pretty obvious. The other one's a 2 or a 1. It's going to be an 80 or 60. So I need you to at least, what I'm trying to say with this is, I need you to at least try everything. If you at least try everything, you're going to get a minimum of 60 on every single objective. Just show us that you're working on things, that you're keeping up with what you're supposed to be doing, and do your work. If you don't even try, it's a 0. That's a big cliff from a 60 to a 0. 0's tough to recover from. I don't want to see any 0s from any objectives throughout the semester. And I'll hit you with the 0 to emphasize that. At least make an attempt to complete everything. Each objective will have a testing procedure attached to it. This is exactly what the TAs are going to go through when they grade your homework. So the TA is going to follow these steps as written, and I don't give them any extra information about how to grade, except when they'll have questions, we'll have dialogue, but I don't have a separate document with grading rubrics or anything. This is the grading rubric. This is exactly how the TAs are going to grade, and I'm going to give this for every single objective on every single homework. So you can write your code for this objective, go through the testing procedure yourself, and you know exactly what the TA is going to do, what they're going to see, what they're going to verify, and you can know what to expect in terms of grading. So I want to make the grading very clear on how you're going to be graded by giving you the testing procedures. When is the first assignment? I mean, it's released right now. You can get it right here. And the due dates are all listed. Each homework is due a week after the content for that homework ends. Okay. Let's get into some content. Unless I missed anything. ID is up to you. Whatever you want to use, or if you don't want to use an ID, language is up to you. Whatever you want to use. Very open-ended in that regard. I'm not going to tell you which language to use or how to write your code. By this point, you should be able to write code in some way. Pick your favorite way and go with it. All right. I think we're good on that front. So let's talk about... I forgot how to do this. Presentation. All right. Let's go through some slides. You're going to use MIPS. Good luck. And I recommend just using the language that you're most comfortable with, of course. But make sure, just use the language you're most comfortable with. We can talk about that at other times, though. I can give my opinions on languages. I did some of it Monday, but I'll always be happy to talk about it some more. So let's talk about the internet. Today I want to talk about what the internet is. At a very high level, we're going to go through it really quick and not talk about all the low-level details, but I do want to talk about networks, TCP, and IP. So let's talk about a couple of different types of networks. First one is a LAN. This is the one that we mostly interact with. This is the one you're probably most aware of in your day-to-day lives. This is what you connect to when you connect to Wi-Fi. You're going to connect to a LAN, which is just a small, and I use the word small kind of loosely here, group of computers that are all connected through this local network. I say small loosely because, for example, UB's network on campus, that's technically a LAN. That's a local network. It's its own separate operating network that is independent of any other network that exists. So it's technically a LAN. You'll connect all those devices to at least one router. In UB's case, there are multiple routers. In your home, you probably just have one router somewhere in the house. That router is probably a built-in router and Wi-Fi access point, and you connect to that, and then that connects all your machines together, and those machines can communicate with each other. With this, we can't do a whole lot. We can have a shared printer, a network printer. We can play games against each other on this local network, but it's not the most useful thing in the world on its own. The biggest use of a LAN is to take this router and plug that into an ISP network so we can get some good old internet. That's really why we have LAN set up in every house these days, is so we can connect to the internet and connect our network, our local area network, to an ISP, an internet service provider network. And this is where we're talking about a network at a much larger scale. These are the city and regional networks. This is where we're up in the utility lines or buried underground. This is where you can actually see a very large piece of infrastructure that's been built to support a very large network. But the concept is still the same. The ISP has their own routers. These cables are plugged in to those routers, and those cables then plug into our routers or to a modem to convert the signals, and then to our routers. But the technologies are all the same. We're still speaking the same language, which is the internet protocol, which we'll talk about in a second. So it's the same idea. The cables are bigger, the routers are bigger, there are more connections, but it's the same thing. This is the same idea as your LAN, but a company has routed a lot of wires throughout an entire region to be able to connect a lot of people together. So you can play games with somebody across the city from you. And they solve what's called the last mile problem. When you want to connect to your internet's network, the network is already there on your street, and then a technician has to come in, splice in wires to the pole, and then run those wires to your house, route them through your house, hook up a modem, and then allow you to connect to plug into that network. But it's just the same as if you bought a desktop and plugged that desktop into your home router. Same technologies are being used here. Nothing fancy, just bigger scale. When we go a step up from that, we talk about the tier 1 networks. And these are networks that are connecting cities and continents and countries together. These are the very large networks that are running. They'll run cables from coast to coast across large areas of land. But they don't really go into the cities. They'll plug. The ISP is going to plug into one of these tier 1 networks, and then the ISP is going to go house to house and solve that last mile problem. The tier 1 network is worried about connecting those cities together. So just like we pay the ISPs for internet service, the ISPs are paying the tier 1 companies for access to the internet. The ISP itself isn't quite the internet yet, that local regional network, but once they plug into a tier 1, and these tier 1s are connecting everybody, this is where we get the internet as we know it. So the tier 1s are commonly referred to as the backbone of the internet, because this is how we actually connect to everybody on the planet, or everybody who's connected, at least. Every network that's connected to the internet. That means, in a very real sense, that they are connected to a tier 1 network, usually through an ISP. But like in UB's case, UB has a tier 1 internet connection. That means they're plugged directly into a tier 1 network. They don't mess around with FiOS or any ISPs. They don't mess around with that. They just plug right into a tier 1. These tier 1s have peering agreements with each other. So any tier 1 network tends to have a peering agreement with other tier 1 networks that allows them to use each other's networks for free. They could monitor the usage and then bill that time and bill each other. They decided that overhead would be just too much effort, or for whatever reason they decided that's just not gonna happen. So they have peering agreements. They say, let's just call it a wash. Like, if I bill you and you bill me, it's just gonna, we're just moving a lot of money around for no reason. So they have peering agreements, which means they effectively act as one large network. The collection of all tier 1 networks just acts as that backbone of the internet, since they use each other's networks for free. This does increase the speed and reliability. You don't have to worry about, what tier 1 network does your ISP connect to? We don't have to worry about that. As long as they're connected to one tier 1 network, we get the benefit of all tier 1 networks. Feels like you'd be rocking that Comcast. Yeah, they also have a lot of clientele. There are a lot of people using that Wi-Fi all at once. I think the Wi-Fi is the limitation when we have slowdowns on campus, not the internet, not their upload download speed. So a couple tier 1 networks. There are more. You can look at the list, but this is actually most of them. There are not very many, at least in the United States. This is most of the list, and you might recognize a few of these. You'll recognize the tier 1 networks that also tend to act as ISPs or have wireless networks as well, like AT&T and Verizon. You might recognize those ones because sometimes tier 1s see an opportunity in a market, like Verizon did with Fios. They'll see an opportunity and they'll go in and build their own ISP in that region and connect it to their tier 1 network. And as you can imagine, they connect cities together, very large areas of land that they're covering. Very large cables, very, very high bandwidth, ridiculously high bandwidth. Think of how many people are watching YouTube in these cities. These tier 1s can have to handle a lot of data. Is this the same lecture you got 3 years ago? Yeah, kinda. So I did borrow some of the slides from that, most of the slides actually. But this goes at a much faster pace. I cut out most of the slides from the 199 stuff because we can go quicker in this course. So these are a list of tier 1s. You might recognize a couple of these, AT&T and Verizon, I'm sure you've heard of. But the other ones, maybe CenturyLink, but the other ones probably not. Especially L3 Communications. This is the largest tier 1 network in the United States. A lot of your internet traffic is going through L3. And unless you've studied tier 1 networks or you remember my 199 lectures, you probably never heard of L3 before. And they're such a huge part of the internet, which I always find weird because we have internet issues. We love to blame our ISPs and we love to attack them so much, but we don't even think about these players who are, behind the scenes, but much more important, in my opinion, in terms of our internet connections. So the implication here, there's an implication that these networks have to plug into each other. I just use the loose term colloquially, like, they plug into each other. But how do we get networks at this scale to just plug into each other? So that actually happens in places called internet exchanges, and these are usually can be entire buildings. I believe it's at least one floor. For some reason, I want to say the 6th floor of 60 Hudson. Or maybe it is the whole building. I'm not super clear on that. But a large part of this building, at least, is dedicated to being an internet exchange. And that's where just all these cables come in. I don't think this is the exact internet exchange at 60 Hudson, but this is a internet exchange where just a ton of cables come in and they need to be plugged into other networks. So these tier 1s, if they're peering with each other, they have to be plugged in together. The ISPs paying for the tier 1 access, they have to be plugged into each other. And you can imagine just how much of a mess this is to manage all the cables and just physically plugging in two massive networks. And when I showed you the tier 1s, I only showed you tier 1s from the United States, from the continental US. But we all know that the internet is a global thing. We can connect across anywhere in the world. So how do we do that when we have these large bodies of water called oceans that, how are we going to connect those? Well, they're actually same thing, same theory as when you take your Ethernet cord and plug in your desktop to your router at home. Same idea. Of course, it's going to be fiber instead of copper, but we just have giant cables. Plug one end in Europe, plug one end in New York, and we're connected. Plug one end in China, plug one end in California, connected. And these giant cables, these transoceanic cables, are literally that, just cables that plug in continents and cross oceans. to connect across oceans, which is crazy. This still blows my mind that this is, out of all the technology, we like to think of technology as really advanced, and we have all these clever ways to communicate and to get things done. And when it comes to crossing oceans with the internet, having the internet cross oceans, it's literally just plugging in cables. It's not even an underwater pipe hunchingly. It's not even pipe. It's just a cable that lays flat on the ocean floor. They just let it just lay there. Not even a pipe. And that's how we connect content. It's just to get a really long cable, plug in one end, plug in the other end. We're connected. It's just such a silly solution. It sounds like a joke solution. Like if I want to connect to my internet, my neighbor's internet, well, let me just get a really long Ethernet cable and plug in one end and plug in the other end. Like it seems silly, but that's literally what's happening, even at a global scale. For the example with my neighbor, there's a cable that runs underground in front of our house. Actually, we have telephone lines, utility lines. It goes up in those poles, goes over to my neighbor's house, and then goes through those cables over to their house. Like that's how we connect things. So we literally have the world wrapped up in cables, and that's what the internet, in a very real sense, is just a whole bunch of cables that are wrapped around the planet, connecting all these things, and then tons of routers to manage the connections between cables. That's what things is. Just like your LAN in your house, that's how the entire internet works. Routers connecting cables. The cables get bigger, the routers get bigger, the hardware gets more expensive, but it's the same idea all the way up to the global scale. And worth noting, even private companies are running these cables. Well, of course, the tier ones are private companies or maybe public, but companies that are not tier one networks are also laying cables. Google, and I believe Facebook as well, has their own networks. Google has a global network of their own infrastructure, so they don't have to rely on a tier one network. That when Google products, they're always up. You don't have much buffering and stuff. It's because they spent billions on their own global infrastructure. So great, we got the world wrapped up in cables and routers, but how do we do anything with that? So we use all those cables and routers to connect to the apps that we want to use, and the apps are ran in very powerful data centers that are huge buildings like this that are just packed full of servers. Again, just like the LAN is the same idea as the internet on a global scale, the apps that we use, think of YouTube, Twitch, our social networks and everything. That's the same idea as if you write a web app and run it on your laptop and connect to it with localhost. The same idea, except the apps are so large that they need a lot of processing power. So they just have a lot of machines with the same type of hardware, RAM, hard drives, etc. Same type of hardware that you have in your machine, but they just have a lot of machines all plugged into each other to be able to serve you that experience, to serve you whatever app it is that you're accessing, and to store all the data. Think of how many videos are uploaded to YouTube. That's a lot of data storage, so they just have a ton of hard drives in these giant buildings that can process all that data. And AWS. A lot of companies pay AWS to do this for them because, as you can imagine, it's pretty expensive to build a giant building, fill it with machines, and cool all those machines. Cooling is a big question, a big challenge with these things. So a lot of companies just pay AWS and have them build the infrastructure. They have the buildings all over the planet. Or Google Cloud. Google has data centers all over the planet so that they can host your app and have it function the way that you want it to function. How large are these cables in terms of width? The oceanic cables at a couple feet, I believe. When I had this as 199 slides, this is one of the slides I cut, but I showed a video of one of the cables being laid. I'd say it was at least a foot in diameter. and it's just a ton of fiber optic inside the thing. It's just a whole ton of fiber. All right, so that's what the internet is. It's literally cables. It's still, and by the way, one of the underlying themes of this course is I'm going to dispel a lot of the magic of how the internet works. So if you want to think that the internet is this magical cloud that just makes things work and is awesome, you might want to drink away today's memories and then drop the class. But I'm hoping none of you want that. I'm hoping you all want to understand how the internet actually does work. Step 1, wrap the world in cables and plug in a whole bunch of computers to routers. Step 1, done. Drops class. No, don't actually drop it. Or if you do, at least hang out for the lecture still. Learn something. It helps to learn. And lots of redundancy. Yeah, good point. The real master. So it's not like your data is stored. You store data. You upload a YouTube video. It's not like, oh, that YouTube video is on this hard drive on this machine. It's going to be duplicated and spread across many machines using. If you've heard of RAID, RAID has ways to redundantly store data on multiple machines. But they're on the next level of that. They're on distributed RAID, where you're not on just different hard drives, you're on different machines entirely. So if an entire machine or entire rack of servers, or realistically an entire data center, this is what they have to think about. An entire data center is completely wiped out. This whole data center just gets destroyed for whatever reason. They don't want to lose any data. That's the level of redundancy they got to think about. If an entire data center goes down, I did actually it was just a shadow day, but I was talking with developers for a bank, a local bank, and they have all of their data duplicated in multiple data centers just to make sure that they don't lose any financial data, because losing data would be devastating to them. All right, great. We wrap the earth in cables. Go humanity, go us. What do we do now? So how do we actually get things to work and get the apps that we want to be able to actually enjoy the internet? Well, we got to start talking about protocols, which is going to be a large part of this course, is talking about different protocols. We'll talk about IP and TCP today, which are two fundamental protocols for the internet. But you won't have to code those. You'll have to just use whatever library you have that runs a TCP connection, that gives you a TCP IP connection. So, but let's talk about what these are, at least give you some background on what that's doing for you. So first, the Internet Protocol. I'm sure you've heard of this, a lot of this before, but the Internet Protocol is a way to get devices to be able to talk to each other, and how routers are going to route information through the internet. And I'll show some IPv4. If you want to read the actual spec and these RFCs, requests for comments, we'll see quite a few of these throughout the semester, and I'll always link them in the course website if you want to go right to the source, right to the RFC. For the later things, the ones that you'll actually be coding, I highly recommend going through at least some of the sections of those, the ones that we'll be coding. Like when we talk about HTTP, we'll look at that RFC and the sections that define what an HTTP request is. Getting all the fine-grained technical details can be helpful. So for this IPv4, the RFC is 760, and this defines what IPv4 is. And again, there's no magic here for protocols. Every protocol is just an agreement on how we're going to do things. Usually an agreement on how we're going to order information that's moving across the internet. The internet, the cables, they can only transmit bits of information, either zeros or ones, high voltage, low voltage, light or no light in fiber. That's all we can transmit over the internet. So how do we take these ones and zeros and make sense of them? Well, we're just going to agree on some protocols. And as long as we're both speaking, if we have two routers talking to each other and they both speak IPv4, they both follow the same protocol, well, then they can understand each other. They can talk to each other. So the Internet Protocol is going to define how information moves through the internet, and that is through packets and datagrams with a limited size. So you can't send very much information over the internet at one time. Usually, if you have a lot of information to send, or usually always if you have a lot of information to send, if it exceeds the packet size, that's going to be split into multiple packets and then routed through the internet separately. This is a very important part of the internet that lets us share those cables. The fact that the internet is what we call packet modulated, it allows us both to use the same cables at seemingly the same time to us, because when our data is routed, maybe you're watching a high def video on YouTube and I just want to download a PDF. Well, you get a packet, I get a packet, you get a packet, I get a packet. Obviously not exactly in that nice, neat order, but our packets can be mixed together because the internet is just sending one packet at a time and not being too concerned about what information that packet contains. So you can download your big movie. My packets can still get in there while you're streaming that video. And then once I'm done, you can have all the bandwidth back. You just get all the bandwidth. All your packets can get through if we're using all the bandwidth of that. So this is a very important part, very fundamental, very early in the days of the internet, back in ARPANET, this decision to be packet modulated was made, and it's a very important decision, as opposed to like old phone lines where you would call somebody, you would make a connection, and then those two people are taking that wire. That resource is designated to them and only them. No one else can use that cable at that time. With the internet, packet modulated, we can all share this resource in a pretty nice way. These packets contain two chunks of information: the header, which has a bunch of information about the packet, most importantly, the source and destination IP address, and then the payload, which IP does not care about. The payload can be whatever bits we want it to be. The internet itself does not care. It's not part of the internet protocol to care what the payload is. As long as it doesn't exceed the max packet size, we're good. So the payload usually contains more protocols. Usually we have, what we'll see today is TCP. The payload actually speaks TCP, and then the receiver of this packet is going to speak TCP and parse all that payload. But it could be any bits that we want to send over the internet. IP, which is the internet, really doesn't care. So an IP address is going to be the address of a machine on the internet. Anytime you have a device that's connected to the internet, you get an IP address specific to that device. And then that's how people connect to you. I won't bore you with the whole analogy, but it's basically like having a mailing address. Somebody wants to send your machine a message, they send it to your IP, and then the routers know exactly which device out of billions that packet needs to go to. So we have an IP address and then send information to that IP. Large networks will have an IP prefix all of their own. For example, one of Google's prefixes is 172.217. And any of their devices, any device on the internet that starts with this prefix, we know that's a Google device. And the routers of the internet can just look at these first two numbers and send the information to Google, say, Google, take care of this. And then once Google gets it, they can route it to whatever specific device it belongs to. Same with UB. When you connect to UB's wireless, you're going to get an IP address in a certain range that UB controls. And then when you connect to the Wi-Fi, they temporarily assign you one of those IP addresses. And then and that's how you can get information. The routers, whatever app you're connecting to, knows how to talk to you. They'll send information to that IP address. It gets the routers of the internet, give it to the UB network. UB's network knows which exact device to send that packet to because it's the IP address that they assign to you. Problem with IPv4 is there's only 4 numbers. Technically just a 32-bit address, but for humans, we break this into 4 numbers from 0 to 255, instead of just looking at the bits like machines do, like the routers do. So with 4 numbers, 0 to 255, 32 bits, we have about 4.3 billion IP addresses, which is a lot, but it's not enough. That's not enough addresses. When the internet was first being created, this probably sounded like a lot, like 4.3 billion. 4.3 billion people are never going to use this little network tool that we're using over here. But of course, what the internet has become these days, there are billions of people connected to the internet, and most people, at least in first world countries, we have multiple IP addresses. I got my desktop, my laptop, my phone right here. Like we have a lot of we need a lot of IP addresses just per person, which is pretty nuts the way what the internet has become. So we needed a new protocol that has more IP addresses. So a bunch of people got together and said, we're going to come up with a new one. And they came up with IPv5, and then no one liked it. So they came up with IPv6. And this uses 128-bit addresses, which gives us this many total possible clients that can connect to the internet, which is a lot. Like, I'm going to say that's enough. Like, I want to say when IPv4 was first proposed, they were a little naive. They looked at this number and said, that's plenty. We'll be fine. But when I look at this number, we're going to be fine. We're not going to exceed that no matter what ends up happening. This number is more than the number of, at least estimated, number of atoms in the universe. So even if we give every atom in the universe its own IP address, we still ain't running out. We're still going to have enough left to spare to give every atom in the universe enough IP addresses to do whatever it wants. So we're going to be good. We're going to be good. Wait till 2077. Yeah, maybe I'll be wrong. Yeah, I'd be happy to be wrong about that. If some technology comes out where this isn't a big number anymore, that'd be pretty nuts. Transplanetary cables. But even that, when we're talking number of atoms, and the number of atoms is like, oh, maybe actually I might be confusing a little bit. Number of atoms is like 10 to the 70. Maybe we're not quite number of atoms. I'm always thinking 10 to the 128 there. So with these IP addresses, these are pretty much invisible to you if you're just a user of the internet, because we have something nice called DNS, which maps domain names to IP addresses. So whenever we type in something like buffalo.edu, the DNS server gets buffalo.edu, says, oh, here's the IP address for buffalo.edu, and then your browser makes a request to that IP address and does what it needs to do. So the internet needs these IP addresses, and we have this nice DNS server, DNS servers, which make things more human readable, so we can mess with domain names and not IP addresses. But the IP addresses are a fundamental part of the internet. DNS is just there for us humans, so we don't have to remember all these numbers. But you can use IP addresses to go to websites. Instead of google.com, you can type in its IP address and get to the same site. You just bypass by going here, you just bypass the DNS. Not some sites do restrict this. I don't even remember what site this is, but when you go to it, it says we don't allow direct IP access. You have to use the DNS. So the internet protocol, when you have a packet that you want to send over the internet, this is what the header is going to look like, at least for IPv4. The very first thing you have to say, okay, what version of the internet protocol are we using? Is this 4 or 6 for our purposes now? A lot of extra other information, and most importantly, the source and destination IP address. Most importantly, the destination IP address. Where is this going? The routers are going to read this information and then figure out where to send this packet. And this is the bytes in the packet. So like the first 4 bytes of the packet contain the version number. The next 4 bytes contain the IHL. The next 8 bytes, etc. So if you read this many bytes, you know the next 32 bytes that you're going to read is the source address. This is bits, isn't it? The next 32 bits you're going to read is the source address. The next 32 bits you read is the destination address. So when a router gets an IP packet, it knows just by the number of bits that it needs to read, it knows exactly where that destination address is, reads that, sends it on its way. And that's really what most protocols are, especially the ones we'll talk about in this class, is just defining the order of the bits. What does each bit mean? We're going to assign it some meaning, and as long as the sender and the receiver both are reading the same RFC, following the same protocol, they're going to be able to effectively communicate. When a router does need to route one of these packets, it's going to read that destination IP address and just send that packet to its what we call the next hop. It just sends it to the next router of the network based on a routing table, and then completely forget about it. I don't want to talk too much about this slide. I want to get to the next stuff. I'll pick up the pace a little bit here because there's something I want to get to at the end. So that's the internet protocol. That's the entire internet protocol. Routers get this packet with a specific thing and just send the packet off to the next router, and then completely forgets about it and only knows its routing table. By implication, the internet is unreliable. The internet will drop packets, a term you've probably heard plenty of times. The internet will drop packets. Packets will be lost for any number of reasons. And since the routers just send that packet to its next hop, and then forget about it, there's no way to recover from a failure. So, for example, if that next hop never received that packet for any number of reasons, there's no way to detect that through the internet protocol. There's no way to detect that. The internet protocol is just inherently unreliable and will drop packets. That's just a fact of life. The internet drops packets all the time. So our browsers, in our case, but the clients, the software, has to come up with a way to be able to use this unreliable connection in a reliable way, and that's what TCP does for us. TCP is going to give us a reliable way to communicate over an unreliable network, being the internet, using IP. So we can't just use IP alone. We can, but we're going to lose data. We use IP with TCP to have reliable communication. TCP relies on establishing a connection through a three-way handshake. So when a client, like a browser, wants to connect to a web server, it's going to send a sync message. The server is going to respond with its own sync message and an acknowledgement that it received the sync message and speaks TCP. And then the client responds with the same acknowledgement, hey, I also speak TCP. And then once that connection is established through this three-way handshake and the client and server both agree that they're speaking TCP properly, then they can start communicating over a TCP connection, which, among other things, gives us sequence numbers for our packets. So when we send a piece of information, say it takes 100 packets to send this one piece of information, we send all that to the other side of the connection, and each packet can be routed through the internet differently. If for any number of reasons routing tables get updated or whatever, the packets might come in out of order. The receiver arranges them in the proper order, and then if any packets are missing, send a re-request for that specific sequence number. So if you have 1, 2, 3, 4, and then 6, well, hey, I need packet 5. So you send a re-request. Please send me packet 5 again. And then you can resend that dropped packet instead of resending the entire piece of information again. So this gives us a reliable connection. We have the connection. Usually the first thing is, hey, this is how many packets I'm going to send you. So you know if you lost just the last packet, you can still say, hey, I lost the last packet. That one was dropped. So then with this resend and then a combination of resending and timeouts. So if I send a resend request and after the timeout time I don't get a response, I can send another request for that packet. And then eventually we'll get all the packets for that connection. So we can get reliable connection through this TCP. TCP also introduces the idea of port numbers. So if we have multiple things, say have 2 different browsers open and each browser has multiple tabs, how does the internet know where to route those packets? Which process? Well, the internet doesn't, but TCP does, because TCP is going to say send this information to this specific port number. Then your machine, your operating system, will say, hey, I just got a TCP packet for a specific port number. Let me send that to this application. So for our purposes, everything that we talked about today, TCP IP, you can use a library for. And that's the only thing you can use a library for, or except concurrency later, for your homeworks. So if you have whatever the standard way to create a TCP connection, a TCP server, which can connect using TCP sockets that you have for your language. Use that and don't think about TCP. That'll handle the handshakes for you. That'll handle data transmission. It's gonna do all of that stuff for you. You don't have to worry about manually doing the TCP handshake and all that. So that much you can do, and then everything else is going to be built on top of that. So we start with a reliable way to communicate over the internet, and that's it. So we're not worrying about the hardware and that communication level. But we are going to build everything else on top of that. So we are going to build starting with HTTP, we're going to build everything else on top of it. If you do want to learn more about TCP, IP, and many other awesome things, I got a shout out to Modern Networking Concepts. That course will go over like how do routers update their routing tables? How do they know if a router goes down? How do they recover from that? All kinds of really good stuff. If you're interested in the networking side, I'm not going to touch it. I'm going to leave that to 489. But if you are interested in that, go check that out. We're just going to assume that it works and just start with a TCP connection. I forget who teaches 489 these days. So, all right, 3 minutes. I can do this. What else did I want? Oh, I actually closed it. Oh well, we'll get this. Let's move this over here. Oh, yeah, we got there. So I'll give examples. I'll try to mix up the languages throughout class, but I'll give examples of some of the things that I say. Here's an example of a TCP socket server in Python. So here's my Python code, which is largely based on the example for socket server in the documentation. There is another way to set up a TCP socket connection in Python by using the raw sockets. I don't recommend that. Quite a few students used it, including one of our TAs, used that last year. And then when we got to web sockets, it was just absolutely horrendous because it doesn't handle multi-threading like at all. You have to do your own multi-threading, which is not something you want to spend your time doing. Unless you do, I mean, go for it. It is kind of fun. I took a look at it and got it working, but I had fun doing it. But you got a lot of stuff to worry about this semester already. So you can have a threaded TCP socket server using this setup. Pretty easy. So if you're using Python, I would start with this. Check out this documentation and get it running like this. So what this is going to do is set up a TCP server, which is going to run this handle method using an event-based architecture. It's going to handle requests that are sent to it with this method. So once somebody connects to a socket, this kind of hides the actual socket connections, the actual TCP connection from you. But every time you receive information over a connection, you can access who sent this information through this client address and the information that they are currently sending. You can access the socket and this is going to read up to 1K bytes of information that are being sent from that socket. So something that'll come up later in the semester. What if you have more than 1K bytes being sent? Well, we can increase this number, but okay, what if you have a gigabyte being sent? Something we'll have to think about later. What happens when you exceed your buffer. But anyway, this is how we're going to receive information. All the TCP, the handshake, the connection, everything's handled for us in this code. And we're just going to get that information and receive it. So let me exit out of that and run this server, which I didn't add any print messages, print lines or anything for it starting, but you can add your server is started or whatever, listening on port. I usually have, but I just don't for this example. And then we can create a TCP client. Freaking ads and showing up in lecture. Oh, that's why I lost my tab, because I didn't want the ads, so I went to 312.com and then I forgot what I was using that tab for. So this server is listening for any TCP connection. So any client can initiate that three-way handshake, complete the three-way handshake, and then send information to the server, and the server can send information back to that client. I didn't set up TCP client code. We could write a client from scratch and then just send any information to this, but I do have a handy TCP client in my web browser. So in the end, what a web browser is, or fundamentally, like under the hood, what a web browser is a TCP client. It's going to initiate those three-way handshakes, connect to other devices on the internet, and then communicate with that device. Now, usually what this is connecting to a web server, speaking TCP, and then speaking HTTP on top of that. So if I go to localhost 8000, which is where my server is running, that browser is going to send information over that connection. I get 127.0.0.1 because this is all localhost. I'm communicating within the same device. I'm not touching my network at all. And then it sends this information to my web server, and I can print that out and view this information that was just sent over this TCP connection. This is an HTTP request, and this is what we'll be talking about at least for the next few lectures and really for the rest of the course, is what is this HTTP request and how do I send an HTTP response when I get one of these requests, and how do I get this to become a web server that serves my web app.